Hello everyone, Mr. Fawcett here, and we are going to start another lesson on our journey towards understanding what a derivative is. This video will be two parts. The first part will deal with, we're going to eventually get to what the formal definition of a derivative is, and then in part two we'll specifically look at some practice problems using that formula. So before we get going, I want to quickly review what we talked about in our previous video, the relationship between the tangent and the secant lines, and how we can approximate slopes using a secant line, and eventually how we can find the exact slope of a tangent line, which is what we're working towards in calculus. So we have a graph here, and we have a point, right? We have this point C comma f of c. And the question is, how do we figure out the specific slope at that point? Right? Up until this point in our mathematical journeys, we've only been able to find slopes of segments or slopes of secant lines. So we've been able to estimate the average rate of change, or the average slope between 2 points. But unless the function was a constant function, we weren't able to find the instantaneous or the specific slope at an individual point. So the question is, if we can't find the slope of the tangent line by itself, right? Because the tangent line only has one point. And the slope formula, the change in y over change in x, requires 2 points for us to use, right? A y2 minus y1 all over the quantity x2 minus x1. So if there's only 1 point in the tangent line, we're unable to use that formula to find the slope. But what we said was we could use the secant line to start approximating the tangent line. So let me open up this demo for us, and we'll quickly review what we talked about in our previous video. I have gone into much farther depth in our previous video, so I encourage you to watch that if you haven't already. And so here I have an interactive demo, and I can move this point closer and closer to x equals c, or I can move it farther and farther away from x equals c. So as we approach x equals c, the secant line looked more and more like the tangent line, right? When t was, or sorry, I might have said x, I'm moving t. When t was exactly what c was, the two lines were indistinguishable. They were the same line. But we ran into the problem of, our formula for the slope of the secant line was equal to, let me move that t value away so it's easier to see. Right, our slope of the secant line ends up being f of t minus f of c all over the quantity t minus c. And if we move that t value directly on top of c, so t is the same as c, well then we run into a problem, right? Let me get out a pen real quick. So when t is equal to c, we have f of c minus f of c all over c minus c, which gives us 0 over, which is indeterminate, right? So we're unable to find, let's write that all the way out. So we're unable to find the slope of the tangent line just by using this, because we get something that's indeterminate. What we said though is, while we can't just substitute those values in, we can think about a concept we talked about in our first unit of calculus, and that's the idea of a limit. So as I move t closer and closer to c, right, it looks like the secant line is going to become the same as the tangent line. And that's regardless whether I move it closer to c from the left, it approximates the tangent line, or whether I move it to c from the right. Right, so this is just kind of showing the one-sided limits are going to be the same because the slopes approach the same number. They both approach the slope of the tangent line regardless from what side you come in. So we know that there's a slope for the tangent line. We can see it on our paper. But the way to find it is not to just use the slope formula. It's to use the limit of the slope formula. So while the slope of the secant line is just the change in y over change in x, the slope of the tangent line, so slope of tangent line, is going to be limit as t approaches c of f of t minus f of c all over the quantity t minus c. So this is where we left off in video 1. If we add that limit notation in front of it, that will allow us to find the slope of the tangent line, which is what we're after. We haven't practiced using this formula or anything. We were just able to come up with it. And you may wonder why we're not doing a one-sided limit, right? Because from the graph, it looks like we're just approaching from the left. I move my t value. Oh, I got to move it from down here. But the problem is, or not the problem, but the reason is t just stands for a random number, right? So t could be on this side, it could be on this side of c, and it has to work, right? This equation has to work regardless of what side we're on. So it has to work if we're approaching from the right, and it has to work if we're approaching from the left. So that's why we don't have a one-sided limit, even though in each individual case, it's going to come in from one side. But when we think about a general rule, the slope of the tangent line doesn't change regardless of what side you approach it from with your secant line. Okay, so just a little review from part 1. Let's go back. Let's clear this. Let's go back to our notes. And we just kind of discussed all these answers. You could write down the slope of the secant line, and then we discussed how we could take the limit of that expression to come up with the slope of the tangent line. All right, let's look at a slightly different example so we make sure we understand it more completely. I encourage you to work through this example on your own. The only thing that I will give you is which point you should put where, because I don't think that's very clear, and it's not necessarily what I want you to spend a bunch of time focusing on. We're eventually going to find the slope of the tangent line at h. So this has got to be h because that's where the tangent line is, right? The red line is the tangent line. It only intersects the function once. So this is going to be our point h comma f of h, and our point up here will be our x comma f of x. This is the point that we're moving to approach h. So think about questions 2 and 3, take some time to write down answers, and then come back and see how you did. Okay, so part 2, or question 2, said write the slope of the secant line. So slope of the secant line, again, just the change in y over change in x. And that's going to be equal to f of x, f of x minus f of h, my y2 and my y1, all over the quantity x minus h. And of course, you could flip both the numerator and the denominator. You could make it f of h minus f of x, all over the quantity h minus x. As long as you flip both, you're okay. That's the slope of the secant line. So if we want to find the slope of the tangent line, right, we just have to make this a limit expression. So slope of tangent line is just equal to the limit, and this is important, x is approaching h, not the other way around. So as x approaches h of f of x minus f of h, all over the quantity x minus h. So if we were to use the thing that I boxed in green, that is a form of a derivative, right? So that's an equation we can use to find derivatives. And again, this word derivative is just the slope of the tangent line at any given point on the function. Let's look at this graph in one other way, because the definition of a derivative has multiple ways of being written. So the points are being written in a different way here. And let's quickly talk about those before you work through and find the two equations. So we're going to be finding the slope of the tangent line at x. So this point must be our x comma f of x this time. And which means that this this spot on the x-axis would be x. And then the other point they're labeling as, oops, that's a typo. Let's fix that real quick. Okay, so our point up here ends up being x plus h, comma, f of x plus h. And all that's really saying is that h is just this distance between the 2 points. So this point up here would be x plus whatever that distance is. Okay. Work through numbers 2 and 3. Come up with the slope of the secant line as well as the slope of the tangent line, and then rejoin us. Okay, so slope of the secant line, that's the blue line. Change in y over change in x is equal to f of x plus h. And you can, again, you can do this in whatever order you want. Minus f of x all over the quantity x plus h minus x. Now, the slope of the tangent line, which is what we're really after, is just the limit of that expression. You know what? Let's simplify this real quick before we get to the limit of the tangent line. You'll see why in a second. So this is really equal to, if we look at the denominator, then there's nothing we can simplify in the numerator. But in the denominator, notice that these two x's simplify. So we're left with h. So that is the slope of the secant line. Now, you'll notice we are moving, we're moving this point along our function until we get down here. So we're essentially pushing h, that distance between x and x plus h, that is being pushed to 0. So going to 0. So when we do this limit expression, slope of the tangent line is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So this one may look a little different because in our previous examples, we've always had like h approaching x or x approaching c. But this time we're just rewriting it in a way where we're looking at the distance between the 2 points and we're closing that distance down to 0. That's why h is approaching 0 here. Okay, let's finish off this video by formalizing our definition of the derivative. All right, so you may want to just copy everything down and then join us for the discussion afterwards. Pause the video, feel free to do that, and then come back. One of the new things we're talking about is the notation for a derivative. So when we're talking about the derivative of a function, we have this little tick mark up here, right, that we add to the function. This is read as f prime of x. That little tick mark means we say f prime. So let f prime of x be the derivative of a function f of x. And then we have two definitions of a derivative down here. And both of these are talking about how to find the slope of a tangent line. Now the difference between these two is that the green one will give you the general derivative. So that means that it'll give you the function of the derivative, which means that you would then substitute in a value for x to find the derivative or the slope of the tangent line at a specific point. The one below it in brown or maroon, if you already know where you want to find the derivative at, I would use the one below, because that is going to give you the value of the derivative at a specific x value, whereas the one above it in green will just give you the general derivative function. So again, we know that derivative is the slope of the tangent line. Let me draw you a little graph, and then let's talk about this notation a little bit more and what it means when we're talking about derivatives on a graph. So let's say I have a function. Let's say I have a point here. Let's call this 5. We'll call this function f of x. And I want to find the slope of the function specifically at this point. So, right, I can represent it using a tangent. That's not a great tangent line. Let's try a little bit better. That's a little better. So the slope of the tangent line, the notation for that, right? This slope would be equal to f prime of 5. Okay, so that's just another way of writing what the slope of the tangent line is at a certain point. If I was talking about this point right here, okay, and I try to draw a reasonable tangent line. Let's call that point 2. So the slope here would be equal to f prime of 2. So this notation, f prime, f with the little tick mark, just represents what the derivative is. Again, the derivative is just the slope of the tangent line at a specific point of the function. All right, this is Mr. Fawcett. I will see you in the next video for some practice.